In Module 6, we're going to turn our attention to the inherent beauty in molecules, or, if you like, the symmetry that one can find in them. Our learning goals for this particular video are to recognize and characterize reflection symmetry, rotational symmetry, and inversion symmetry in both 2D and 3D objects. So what is symmetry? Symmetry arises when we have an object that has repeated patterns that can be transformed into one another via some sort of operation. These symmetry elements could include a reflection, a rotation, or an inversion of that object. The key, though, is that the object must have the same appearance before and after that operation related to the symmetry element has occurred. So let's start setting some of our rules for vocabulary in this study. A symmetry element is a geometric object that defines a symmetry relationship. So it could be a plane, it could be a line, or it could be a point. A symmetry operation is a transformation of the object into an equivalent version of it that uses that symmetry element as a guide for it. So let's start illustrating this with some real examples. Which of these figures has a reflection symmetry? Okay, we can say that a reflection symmetry is one that has a line that divides two equivalent halves, and that would be a line of reflection. So for example, we would see a line of reflection in the isosceles triangle at the far left. We can also see a reflection line in the rectangle, but it has two of these, one that's vertical and one that's horizontal. And there's an infinite number of reflection lines in the circle because it doesn't matter how they're oriented, as long as they go through the center of the circle, they represent a reflection of the circle. In 3D, we have similar properties. These can also have two halves that are mirror images of one another, but they're divided by reflection planes, which we denote as sigma. Sigma is the symbol that we use to denote these planes. So let's look at some examples. So here we have a rectangular prism. Now we could cut that prism in half this way, and the two halves on either side of that plane are reflections of one another, so that's a reflection plane. We could also draw a reflection plane that cuts it in half this way. The top half and the bottom half are again equivalent to one another, reflected through this reflection plane. We can also draw one that is in the page of our diagram, so the front half and the back half are reflections of one another. So there's three different reflection planes that we can find in this particular object. Okay, if we consider a triangular prism, we also have a number of reflection planes. One that cuts this right down the center of the picture, as shown on the left, and then others that are oriented along axes that also cut the figure in half and have equivalent halves on either side. We also have a symmetry due to rotation. And it's easy to see in 2D. Is whenever an object is indistinguishable after it's a rotation through some angle less than 360 degrees. So for example, let's take this rectangle. If we put a dot in the middle of the rectangle and rotate the rectangle about that dot by 90 or 180 degrees rather, we'll get a similar rectangle, but you'll notice because I've labeled the positions that rotated rectangle has the corners now have flipped positions. This is something that's called twofold rotation symmetry because we've rotated by 180 degrees, which is equal to 360 degrees divided by 2. That's where it gets the name twofold. What if we had a hexagon? Okay, once again I've labeled the vertices. Now we can rotate by 60 degrees to get an equivalent object, and another 60 degrees, and another 60 degrees, and so on. So this is said to have sixfold rotation symmetry because 60 degrees is 360 divided by 6. So it's in each of these cases we're rotating by some angle that's a fraction of 360, and that gives us an equivalent object even though we have in fact switched the positions of the vertices. In 2D, the symmetry element for rotation is a point about which the object is rotated. So the point that's drawn in the middle of each of these figures is the symmetry element for rotation. In 3 dimensions, they also can have rotational symmetry, but now the symmetry element is going to be a line or an axis of rotation. and it's usually denoted by the symbol C sub n, where n is the order of that rotation. So for example, if we had an equilateral triangle, we would have a C3 axis that runs right through the middle of this, giving it threefold rotational symmetry. If we lay that in a plane, the axis that we're talking about is the one that runs right up to the center of the plane, and as I said, it's labeled C3. What would happen if we had a triangular prism? What sort of rotation symmetry elements would we have in this case? Well, we have the C3 axis still running through the middle, but we also now have C2 axes that run perpendicular to the C3 axis. There's one that penetrates the middle of each side and the opposite vertex of the prism. Our last example of a symmetry element is inversion, and let's look at inversion symmetry in 2D first, and then we'll later look at 3D. Inversion is the process of taking every point on an object, projecting it through the middle of the object to the opposite side, to a spot that is equidistant from that center. If the result of doing that inversion is an object that is indistinguishable from the original, then it has inversion symmetry. We call that inversion symmetry. We denote it by an inversion center that is called I. And we can see some simple examples in 2D. If I took a rectangle, that inversion center would be right in the middle. We would invert each of the vertices through that center to the opposite side, and we would end up with this rectangle. We can also do this with a circle, and of course, again, the center of the circle is the inversion center for this, and every point on the circle has a companion point on the other side, so as they're inverted, they are converted into one another. 3D objects can also show inversion symmetry. In this case, we also have a point or center of inversion, and we also use the symbol I to denote it. Platonic solids are a great example of 3D objects with inversion symmetry. So for example, a cube. And in this case, we've labeled the vertices so that the two A labels connect points that are inversion opposites of one another, as are B's, the C's, and the D's, all of them inverted through the center of the object. An octahedron similarly has this, and again we've labeled the vertices of the octahedron so that the two A's represent inversion symmetry related points. The two C's represent that, as do the two B's. As an activity, I want you to take a look at these two objects. One is a pentagonal prism, the other is a hollow cylinder, and decide what the symmetry elements that are present in these two objects are. Now you can pause this video and take a moment, and we'll come back with the answers. All right, hopefully you figured out that this pentagonal prism has 5 sigma reflection planes. Each of these are perpendicular to the pentagon face. There's one sigma plane that is parallel, that cuts the object laterally in half. There is one C5 axis that runs up to the middle of it. There are going to be 5 C2 axes that connect each of the vertices of the pentagon and the opposite side, but there is no inversion center in this pentagonal prism. What about the hollow cylinder? Well, in this case, we have a reflection plane that's perpendicular to the cylinder and basically cuts it laterally in half, and an infinite number of sigma planes that fall along the axis of the cylinder. There's one C infinity axis that runs right through the middle of the cylinder, and an infinite number of C2 axes that run perpendicular to that C infinity axis. This one does have an inversion center, and it's where these two axes intersect one another in the center of the object. I hope you've picked up a little bit about symmetry elements and can learn how to identify them in various objects now.